In this video, we're going to walk through relating the energy of our system to the energy of our surroundings using our calorimetry equation. So mc delta T of our system equals negative mc delta T of our surroundings. So earlier we discussed that the energy of our system is equal and opposite to the energy of our surroundings. So that was from the first law of thermodynamics. And this negative sign is because if our system loses energy, our surroundings gain energy. So we have an equal and opposite process taking place. So we're going to take this E system and E surroundings, and we're going to relate it to calorimetry. So when we talk about the change in energy, we're really talking about the heat change of our system. So we're going to replace delta E with Q. So we can say that the heat change in our system is equal to the negative heat change of our surroundings. Again, equal but opposite. So we can expand. We know that Q equals mc delta T, so we can now expand on both equations. So we can say that the heat, the mass times the specific heat capacity times the temperature change of our system is equal to the negative mass times the specific heat capacity times the temperature change of our surroundings. And it's going to be really important, we're going to go through some examples, to assign system and surroundings, because when we do so, this specific heat capacity and the mass are also of the system. So it's easy to make some mix-ups because you have two masses, two specific heat capacities, two temperature changes. So really important to understand what is system, what is surroundings. So we're going to look at an example scenario here. This is not a question, so it's already solved. We're just going to break everything into system and surroundings and show that the two are equal but opposite. So the scenario is a 10-gram piece of tin was heated in a flame to 1200 degrees Celsius. The tin was then transferred to a calorimeter containing 200 milliliters of water at 20 degrees Celsius. The final temperature of the water, and therefore the tin, was 23.2 degrees Celsius. So the two systems come into equilibrium with each other. That's why their final temperature is the same. So we're going to start by assigning our system. Now, it doesn't really matter which one you call system or surroundings here, provided that you're consistent. So I'm going to call our system the tin and our surroundings the water. This is going to be helpful for when we move on to enthalpy problems. So the system will be our tin and the surroundings will be our water. So the mass of our system is 10 grams. The specific heat capacity of tin is 0.227 joules per gram degrees Celsius. And our temperature change, so that's going to be TF, the final temperature, minus TI, the initial temperature. So our final temperature is 23.2 degrees Celsius, and our initial temperature is 1200 degrees Celsius. So tin got colder, it lost energy. And our change in temperature is negative 1176.8 degrees Celsius. We're going to do the same thing for our surroundings. So the mass of our surroundings, the water, is 200 grams, because we know that 1 milliliter of water is equal to 1 gram. The specific heat capacity of water is 4.19 joules per gram degrees Celsius. And the change in temperature of our water, again, TF minus TI, is equal to 23.2 minus 20. So we have an increase of 3.2 degrees Celsius. So if we look at these two numbers, we see big change in temperature for tin, smaller for water. But we're going to be able to see that the two are actually equal but opposite. So if we calculate our Q for tin, so mc delta T, we'll have 10 grams times 0.227 joules per gram degrees Celsius times negative 1176.8 degrees Celsius. And we find that the heat or the energy change for tin was negative 2,671 joules. So tin got colder, it lost energy. If we do the same calculation for water, we can see, so we have 200 grams for our mass, 4.19 joules per gram degrees Celsius, and 3.2 degrees Celsius. So when we do that math, we get positive 2,681. So there's a little bit of difference from rounding when I did the math earlier, but we can see that these are in fact equal but opposite.